Imagine you're an engineering student, maybe, or perhaps you're just starting out, an early career professional, really eager to make your mark on the railway industry. You're poring over blueprints, maybe for a new train or a critical piece of track infrastructure. You're completely focused on making it safe, efficient, built to perform, flawlessly for decades. But then this fundamental question hits you. What about the true cost? Over all those decades, it's way, way more than just the initial price tag you see up front. That right there, that's where life cycle costing, or LCC, comes in. Think of it as the ultimate financial roadmap for navigating the incredibly long lifespan of railway assets. So today we're taking a deep dive into railway life cycle cost. Our mission really is to demystify what it actually is, figure out why it has become so absolutely essential in today's, complex railway world, and also understand how it helps make smarter, more sustainable decisions that look way beyond just the initial investment. We're talking about everything, literally every single financial impact, from the drawing board where an idea first sparks, all the way through to getting rid of the asset eventually, and how every decision along that path hits the total cost picture, maybe in ways you haven't even considered yet.
That's precisely it, yeah. In recent decades, the importance of LCC analysis has just, skyrocketed. You've got increased cost pressure on public undertakings, right? And that's coupled with the liberalization of the rail sector, which basically means more competition, the creation of separate legal entities for operators and infrastructure managers. So understanding and actively reducing the total cost over an asset's entire life, it isn't just a smart idea anymore. It's really a non-negotiable requirement for sound financial planning and, frankly, for maintaining a competitive edge. If you're looking to build a career in railways, whether that's in design, operations, management, whatever, grasping this concept isn't just helpful. It's absolutely foundational. It fundamentally changes how you think about value.
So you've really set the stage there on why LCC is so vital today. That makes a lot of sense, but for many of us, I think the term itself can feel a bit abstract. When we say life cycle costing, are we just talking about adding up every single bill that comes in? Is it really that simple?
Not quite. And that's actually a common misconception. LCC is the sum of all costs that occur over the entire lifespan of a product, right from its conception to its end-of-life disposal. And this is a crucial distinction. It does not consider revenues generated by the asset, nor does it factor in depreciation. Think of it more like the total cost of ownership. It's an economic method, really, for systematically evaluating costs across the whole life cycle, or sometimes maybe just a specific defined portion if you're analyzing a particular project or upgrade. It's all about looking at the full financial commitment over the long haul, not just the sticker price you pay on day one.
Okay, so it's truly a journey then, not just a single snapshot in time. Our deep dive reveals that industry standards identify 7 key phases for a railway asset's life. Tracing this full financial commitment you mentioned, let's maybe walk through these stages.
Yeah, absolutely. And these phases, they're distinct but fundamentally interconnected steps in an asset's journey. Understanding them is really key to mapping out those costs effectively. First, we have the concept and definition phase. This is where the initial idea for an asset is born, where the fundamental needs are identified and the basic requirements what the asset absolutely must do are laid out. It's essentially the strategic blueprint stage. Second, design and development. Here, that initial idea gets fleshed out into detailed plans, engineering specifications, maybe even prototypes. This is where the technical specifics and choices really take shape. It's where a lot of future costs get locked in, actually. Third is manufacturing and construction. This is the physical creation part, building the train cars, fabricating components, laying the track, erecting signaling systems, bringing the design into physical reality. Fourth, assembly and integration. This phase is all about bringing all those manufactured components and systems together, making sure they work seamlessly as a complete operational whole. Think of it like the final assembly line for an entire train, or connecting all those disparate pieces of track infrastructure into a functional network that actually communicates and works properly. Fifth, operation. This is when the asset is actively in use, running trains, managing routes, transporting passengers or freight. This is its primary productive phase, really, the whole reason it was built in the first place. Sixth, maintenance. Now, this runs concurrently with operation, obviously. It's all about keeping everything in peak working order. It involves inspections, preventive measures, repairs, all to ensure continued performance, reliability, and, above all, safety. And finally, phase 7, disposal. This is literally the end of the line. It involves decommissioning the asset, dismantling it, and handling any remaining materials or components responsibly, often sustainably too, which has its own costs. And while these 7 are kind of the standard framework, you have to remember, depending on the specific LCC analysis scope and the particular asset you're looking at, these phases can be adapted, sometimes broken down even further for more granular analysis.
That makes incredible sense. It really highlights the sheer longevity of these assets we're talking about, decades. But this brings up a crucial question for me. Who's footing the bill or making the key decisions in each of these different phases? Is it always the same entity, or does that responsibility shift around quite a bit?
That's an excellent question. And it points right to a critical complexity in understanding railway LCC, especially, as I mentioned, in today's liberalized rail sector. The responsibility typically does shift across these phases. For concept and definition, it's usually the rolling stock operator or perhaps the infrastructure manager who takes the lead. They're the ones identifying the operational need, setting those initial high-level requirements. Then, for design, development, manufacturing, and assembly, those next 3 phases, the railway industry itself, often specialized contractors like train manufacturers or large construction firms, they largely handle these. They bear the direct costs of creating the asset. However, the infrastructure manager or rolling stock operator then pays an acquisition price for the completed product. This typically happens at the handover point between Phase 4 assembly and Phase 5 operation. So while the manufacturer incurs the cost during those early phases, the operator or manager ultimately covers those LCCs indirectly through that initial purchase price. Does that make sense?
Yeah, it does. So the upfront cost reflects those earlier phases indirectly.
Exactly. And then for operation, maintenance, and disposal phases 5, 6, and 7, the infrastructure manager or the rolling stock operator typically assumes direct responsibility. These are the long-term running costs, right? The expenses of keeping the asset productive over potentially many decades. And an important trend we're seeing is the rise of maintenance contracts, often with the original manufacturers or sometimes third-party specialists. In these arrangements, the manufacturer or a contractor will perform maintenance for a defined price per performance unit, like say per train kilometer traveled or per year of operation. Now, while this shifts the direct management of maintenance, the operator is, of course, still paying for it, just in a different contractual way. And a key concept here, something really worth focusing on, are what we call ownership costs. These are specifically the costs incurred during phases 5 through 7, operation, maintenance, and disposal. These ownership costs often represent a truly massive portion, a huge chunk, of the total LCC for these long-lived railway assets. And because they're so substantial and accrue over such incredibly long periods, they frequently receive distinct and very significant attention in LCC analyses. They're often the main target for optimization efforts.
Okay, so we're talking about a very clear, structured approach here, not just random cost tracking. Is there like a defined process or a standard methodology that railway companies typically follow for LCC analysis? It sounds like it can't just be a quick back-of-the-envelope calculation.
Absolutely not. No, you hit on it perfectly. It's a rigorous methodology. Industry standards, like the IEC 60300-33, essentially provide a comprehensive roadmap for doing LCC analysis properly. And it's not just a one-off calculation you perform once and then file away. Instead, it's designed as a systematic and, crucially, often cyclic procedure. It should be deeply integrated into an enterprise's strategic and financial planning. Think of it like a continuous feedback loop. You're continually refining your understanding of costs as more information becomes available throughout the asset's long life. This iterative approach ensures the LCC analysis remains relevant, accurate, and genuinely useful for making decisions down the line.
That sounds incredibly robust. A feedback loop makes a lot of sense given the timescales. So at a high level then, what are the general steps involved in this systematic LCC analysis process? Can we break that down?
Sure. At a high level, the LCC analysis process typically involves 5 main interconnected steps. Think of it as a cycle. First, it all kicks off with planning the analysis. This is where you set the entire stage. You establish the organizational context, like what part of business this analysis applies to. You identify the specific alternatives you want to compare. You clearly define the precise scope and objectives of your analysis, and you assemble the right team with the necessary expertise. Very important. You also need to pin down any constraints you're working under, budget, time, whatever, and determine the relevant financial parameters. Things like discount rates or inflation assumptions that will apply over potentially decades. It's really about getting all your ducks in a row before you start crunching numbers. Second, define the analysis approach. Here you establish the specific rules and methodologies you'll follow. This involves selecting or sometimes even developing an appropriate LCC model. You create a detailed cost breakdown structure, which we'll definitely dig into in a moment. You identify areas where you expect uncertainty, and you determine the precise methods you'll use for estimating each cost element. This step is all about ensuring consistency and transparency in your calculations. Everyone needs to be on the same page. Third comes the performance of the analysis. This is the actual heavy lifting, right? You actively collect all the necessary cost data. You meticulously aggregate those costs by life cycle phase or maybe specific time periods. And then you perform the actual LCC calculations. A really critical part of this step is also performing what we call sensitivity analyses. This helps you understand how changes in your key assumptions or parameters, maybe a small shift in energy prices or different maintenance intervals, might significantly impact the overall LCC result. It shows you where your analysis is most vulnerable to change, which is vital for risk assessment. Fourth, you move to the finalization of the analysis. Once the calculations are done, you rigorously review the entire analysis. You check its integrity, assess whether your initial objectives were actually met. You identify any follow-up actions required, you thoroughly document everything from input data to assumptions and results, and then you formally publish the results internally. You need to inform decision makers across the organization. Transparency and clear communication are absolutely vital here. And finally, fifth, the update of the analysis. This is where that cyclic nature I mentioned earlier really comes into play. LCC isn't static, it can't be. You periodically need to refresh the underlying data and reevaluate the LCC as conditions change, or as you gain more operational experience with the asset, or maybe as new market information becomes available. This ensures the LCC remains a living, breathing document that continually provides value for ongoing financial and strategic planning. It's an ongoing commitment, definitely not a one-and-done report you stick on a shelf.
That's a truly detailed and comprehensive process. It really paints a picture. But it makes me think, how does this theoretical framework actually play out on the ground? Does the approach to LCC analysis change depending on whether you're, say, sketching the initial concept for a new train or actively running that train every single day?
Yes, absolutely. That's a key point. The application of LCC analysis needs to be smartly adapted to the current life cycle phase. And the reason is precisely because the costs that you can actually influence vary significantly depending on where you are in the asset's journey. You can think of costs in maybe three distinct buckets. First, you have past costs. These are costs that have already happened. They've typically been paid. They're well-known, documented, proven. The critical point is, by definition, they cannot be influenced anymore. They're sunk costs. You account for them in historical analysis, but you can't change them going forward. Second, current costs. These are costs determined by current activities within the present life cycle phase. They're generally well-known, and importantly, they can often be influenced, maybe by optimizing current processes, improving purchasing strategies for materials, enhancing operational efficiency, things like that. However, inherent costs that resulted from prior design decisions or fundamental system properties locked in earlier, those are much harder to change at this stage without significant rework or investment.
Third, and these are, well, the exciting ones from an LCC perspective, future costs. These are costs that are typically not yet known, but crucially, can be heavily influenced by decisions you make today. They must be estimated well in advance. And this is precisely where LCC provides its biggest, most strategic value. By estimating and understanding these future costs, you can make incredibly informed decisions in the earlier phases concept, design that really minimize the total cost of ownership over the asset's entire decades-long life. Let's really deep dive into how LCC is specifically applied in those different phases of a railway asset's life, and why it matters so much in each one. It's quite illuminating. So in the very early stages, during the concept and definition phase, the product is just an idea, right? Maybe a vision for a new high-speed train or a reimagined signaling system. Experience with this specific new product is usually low, maybe even non-existent at this point. However, this is exactly where crucial RAM targets, that's reliability, availability, and maintainability, the overall LCC targets, must be defined. Operators need to gather extensive market information, maybe using analogies from similar products or sophisticated parameterization methods to estimate these future costs. Now, what's critically important here, especially for you as railway engineering students and professionals, is that these LCC targets need to be thoroughly documented. And especially if you're commissioning design, manufacturing, or even future maintenance work to external contractors, they absolutely must be contractually agreed upon. This isn't just a wish list. It lays the concrete financial groundwork for the entire project's long-term economic success. You need that commitment up front. Okay, moving into the design and development phase. Those LCC targets defined earlier, they're now meticulously apportioned, broken down to specific systems and subsystems within the detailed design. Think engines, bogies, control systems. Their achievement is rigorously controlled through continuous design reviews at every single stage. A persistent feedback loop is absolutely essential here to ensure ongoing compliance with those agreed-upon LCC values. This means the LCC analysis is continuously updated with refined estimates as the design matures. For example, if a design choice suddenly increases predicted maintenance costs, that feedback must immediately trigger a reevaluation. Is it worth it? Can we mitigate it? The estimated values for future life cycle phases have to be consistently checked for plausibility and meticulously prepared as refined input for the next phase. It's a really dynamic process of continuous refinement and financial foresight baked into the engineering. Now, during the manufacturing and construction phase, the focus shifts quite a bit. It moves from theoretical estimates towards verifying the LCC based on the actual RAM characteristics of components and subsystems as they are physically produced. You're now gaining real, tangible data from the production process itself. Things like actual failure rates of manufactured parts coming off the line, the measured energy consumption of specific components under test, or their precise lifespan under controlled pest conditions. This real-world hard data feeds back into and critically updates the LCC analysis, refining those future cost estimates with significantly increased accuracy. This is truly where the theory of LTC starts meeting the hard reality of production. The assembly and integration phase is all about the entire system coming together, functioning as one complete entity. Here, you're rigorously verifying the RAM's characteristics, reliability, availability, maintainability, and safety, and the LCC characteristics of the entire integrated system, not just the parts. Information from system-level verification tests like overall failure rates for the assembled asset or its total energy consumption in simulated runs is collected and analyzed. This is often the critical phase where the crucial operation and maintenance cost targets can be finally determined, locked in, and contractually agreed upon between all the parties involved. It's kind of the moment of truth for predicting those long-term running costs before handover. And finally, in the operation and maintenance phase, once the asset is operational, out in the field doing its job. This phase is all about collecting actual operating experience, real-world data. The LCC analysis should be updated cyclically, maybe annually, maybe more often depending on the asset, to support ongoing business planning and budgeting processes. A specific update is also incredibly valuable before major revisions or renovations or maybe fleet modernizations, because it helps in selecting the most cost-efficient tasks and materials for that planned activity. Should we overhaul or replace? LCC helps answer that. Crucially, the collected data from this operational phase then becomes invaluable input for new railway projects and concepts. It effectively closes that loop I mentioned, making future LCC analyses even more precise and effective. It's a continuous learning process, feeding experience back into design. Now, to make this entire LCC framework work effectively, you need more than just a process map. You need robust methods for evaluating costs and critically strong quality control throughout the whole thing. When it comes to methods for cost evaluation, remember, railway companies manage vast and incredibly diverse portfolios. Entire fleets of trains, thousands of components, hundreds, thousands of kilometers of lines, various types of equipment. It's complex. Accurately determining costs is absolutely key, and the underlying data must be up-to-date and valid. Common methods for estimating costs include: we have engineering practice. This bases estimates on known product or service costs derived directly from operational accounting or historical project data, essentially leveraging your own hard-earned historical information and internal expertise. What did it cost last time? Then there's analogy. Here, you use known costs from similar or perhaps scalable products or services. For instance, if you're planning a new generation of a regional train, you might look at the costs of the previous generation and adapt them based on anticipated changes in technology or materials. And finally, parameterization. This is where costs are determined by cost estimating relationships, or CERs. This often involves mathematical models, where costs are a function of certain design or operational parameters, for example, cost per kilowatt hour of energy, or cost per ton kilometer transported. It's more analytical. It's often incredibly helpful, by the way, to use redundant sources, or even different methods in parallel, especially for the most significant cost parameters, the big hitters. This is because collecting accurate input data can often be the weakest link in any LCC analysis. It's challenging. So cross-referencing helps mitigate that inherent risk. And beyond the methods themselves, quality assurance is paramount. It has to be. Just like any high-stakes engineering or safety process in railways, LCC analysis demands robust quality management. Standards like ISO 9001 for general quality management and ISO 55000 for asset management provide excellent frameworks here. Key aspects for LCC quality include ensuring that staff performing these complex analyses have the necessary knowledge and competence, maintaining clear and consistent communication, especially vital with external contractors and suppliers, robust control over all documented information, version control, traceability, it all matters, and ensuring the secrecy and integrity of sensitive cost data. Ultimately, every LCC analysis, including all its underlying input data and assumptions, must be rigorously reviewed and thoroughly documented. This isn't just bureaucracy. It ensures credibility, reliability, auditability, which is vital in large-scale public and private railway operations where huge sums are involved.
Okay, so after all this effort, all this meticulous planning, the detailed analysis, the quality control, there must be some really significant benefits, right? What are the main objectives companies are actually trying to achieve with LCC analysis? What's the big payoff?
You're absolutely right to ask about the payoff. And yes, there are huge benefits. LCC analyses serve, I'd say, four primary, incredibly vital objectives for the long-term health and competitiveness of railway operations. First, budget and project planning. LCC is absolutely essential for both short-term tactical budgeting and long-term strategic financial planning. It helps operators and infrastructure managers accurately estimate required future budgets, everything from fleet renewals to track upgrades. It lets them assess the profitability of potential projects and confirm their overall financial feasibility before committing massive resources. It's really about looking decades ahead to truly understand the full financial commitment and avoid, well, nasty surprises down the road. Second, and this is a crucial driver for innovation, is cost reduction. LCC analyses help identify the major cost drivers within a product or a system. By mapping out all the costs across the entire life cycle, it forces and encourages a big-picture view of total costs. This allows organizations to pinpoint exactly where efforts to optimize and reduce expenses will have the greatest, most leveraged impact. It's about finding those hidden inefficiencies, maybe in maintenance or energy use, and targeting them effectively. Third, and perhaps most impactful for decision-makers, it's about decision-making. LCC provides a rigorous, quantifiable economic assessment of different alternatives. It enables companies to find the most cost-efficient option over the long term. Whether it's choosing between suppliers or different technologies or even alternative maintenance strategies, LCC provides the hard, quantifiable financial data needed to make informed choices. Choices that truly deliver the best overall value over the asset's entire life. It moves decisions beyond just gut feeling or focusing only on the upfront price.
Yeah, when you mention cost reduction and big picture, that really highlights, for me, a fundamental shift in thinking, especially for railways. For these assets, which last for decades, sometimes 50 years or even more, this must be particularly impactful. I can imagine the traditional procurement mindset, just getting the lowest purchase price, might really clash with this LCC approach.
Oh, absolutely. And here's where it truly gets interesting. It's a point that often surprises people new to LCC. In the past, procurement decisions often focused almost exclusively on the acquisition costs. What you paid up front for any train, a signaling system, a piece of track. Just get the cheapest deal today. The ownership costs, that vast portion that accrues over 20, 30, even 50 years of operation and maintenance, were often secondary. Sometimes underestimated, sometimes even completely overlooked in the decision-making process. But LCC analysis forces a profoundly different, and argue much healthier, perspective. It helps you clearly see the economic equilibrium, that critical trade-off between potentially higher acquisition costs, which are very often associated with higher quality components, greater built-in reliability, superior maintainability, and significantly reduced ownership costs over the asset's very long life. It's a holistic view that actively challenges that often short-sighted focus on just the initial price tag.
So essentially what you're saying is a more expensive train today could actually be the cheapest train over its 50-year life. Investing more upfront in better maintainability or reliability during design can genuinely save money in the long run. That sounds counterintuitive for some procurement folks, maybe, but incredibly powerful if it holds true.
Precisely. It's a core tenet of LCC, and it absolutely holds true in many, many railway applications. Improving product quality, for instance, might mean more engineering hours during the design phase, or the careful selection of more expensive, higher quality materials during manufacturing. This directly increases the acquisition cost you pay at the beginning, no doubt about it. However, this upfront, strategic investment directly translates to things like lower failure rates down the line, potentially less energy consumption during operation, and significantly reduced maintenance needs over the asset's entire life. Less downtime, fewer repairs, cheaper running costs. The overarching goal of LCC is to optimize the total LCC to achieve the minimum overall cost, not just the lowest initial price. This is exactly why LCC target values, or specific parameters that directly influence LCC like reliability targets, are increasingly becoming standard requirements in contracts and tenders today. It's forcing manufacturers to design for lifetime value, not just initial affordability. It's a smarter way to buy.
Okay, that makes a lot of sense. And beyond just general cost reduction, how does LCC analysis specifically aid in making those really critical, maybe complex choices in railway operations, like choosing between technologies or suppliers?
Yeah, for decision-making, LCC is incredibly powerful because it provides that quantitative objective framework. It moves beyond just qualitative assessments or gut feelings. It really helps companies make difficult choices between a wide range of alternatives, such as comparing similar products from different suppliers. Which supplier genuinely offers the best long-term value, considering maintenance, reliability, etc., not just the cheapest initial price. LCC can reveal that. Evaluating different technologies. Should we opt for a new, potentially more expensive braking system if it promises significant long-term maintenance savings and maybe improved safety performance? LCC helps quantify that trade-off, deciding between acquiring a brand new product versus undertaking a major refit or upgrade of an existing one. What's the true long-term cost benefit of each path over the remaining life? LCC provides the basis for that comparison, assessing various design solutions for even a single component or system. Which design is truly the most cost-efficient over its entire life cycle when you factor in manufacturing, operation, and maintenance, and even choosing between different maintenance or operating strategies? Should we pursue a more intensive preventive maintenance schedule if it demonstrably prevents far more costly corrective actions and reduces operational downtime? LCC helps model those scenarios. And crucially, when you're comparing alternatives, you don't necessarily need to calculate all costs for every single option from scratch every time. You can often focus only on the differences between the options to establish a clear economic ranking. This significantly streamlines the analysis, making it more practical. However, it's absolutely vital that all alternatives you consider must first meet all operational, technical, and safety requirements. Those are non-negotiable gatekeepers. LCC then provides the essential economic input for a broader cost-benefit analysis or maybe a utility analysis, helping to ensure the decisions are well-rounded and consider more than just the immediate financial outlay.
Right. To actually do this kind of analysis, you need a way to organize all those potential costs across all those different phases we talked about. It sounds like a truly massive undertaking, almost overwhelming, just thinking about tracking everything.
It is, yeah, it can seem that way. And that's precisely why a cost breakdown structure, or CBS, is the absolutely essential framework. You have to have it. Think of it as systematically categorizing every single potential cost based on the product lifecycle phases. It gives you a clear, granular roadmap of exactly where the money flows over time. For instance, at a high level, for each phase, you'd identify specific cost elements. For the very early concept and definition phase, this includes things like the engineering costs for initial feasibility studies, maybe legal costs for contract negotiations, and the project management overhead associated with just kicking off a major initiative. In design and development, you'd find costs for things like homologation. That's the critical process of getting regulatory approval and certification to ensure the asset meets all safety and operational standards. Plus, detailed engineering work, verification and validation efforts, testing and project management specific to the design phase. During manufacturing and construction, you're looking at the direct production costs, obviously, but also the costs for setting up and maintaining production infrastructure and equipment, quality control expenses, logistics for materials coming in, procurement activities. Assembly and integration involves the labor and production costs related to the physical assembly process itself, the logistics for bringing complex components together from various suppliers, and the planning and support for making everything fit and function correctly as a system. For the long operation phase, you have the direct operational costs like energy consumption for trains, driver salaries perhaps, but also less obvious ones like costs due to non-availability. That's the financial impact of lost revenue or increased expenses when an asset isn't running as planned due to failure. You also have logistics for operational supplies and quality costs related to operational performance. Maintenance is a huge one, as we've said. It encompasses the direct costs for performing routine and complex maintenance tasks, labor, materials, costs for the planning and support of maintenance activities, quality costs associated with repair work, logistics for ordering and managing spare parts inventories, and the costs for the maintenance production infrastructure and equipment itself, the depots, the tools. Finally, disposal. This includes the direct costs of demounting or dismantling the asset at end of life, the cost for residue disposal, which can be significant for certain specialized or hazardous materials, and the logistics related to those end-of-life processes. Now, obviously, this list isn't exhaustive, and it always needs to be adapted for specific applications and the level of detail you need. And it primarily focuses on those direct costs that can be clearly tied to the asset's life cycle.
Okay, so when we talk about LCC with this kind of structure, we're really focusing on those direct attributable costs. Does that mean we're generally not considering things like general company overhead or broader capital costs? Where do those fit in, or do they?
Correct. Generally, when we perform a direct LCC analysis using this kind of detailed breakdown structure, we typically exclude what we might call semi-indirect costs. These would be things like general capital costs across the entire organization, overall company-wide overhead like HR or finance departments, various taxes that aren't specific to the asset, maybe general employee training costs not related to the specific asset, and broad accreditation expenses for the company. Similarly, indirect costs like the general maintenance of IT systems that support the entire organization or the upkeep of the head office building. Those are generally not part of this specific LCC calculation for a single asset or project. The main reason for this exclusion is that these types of costs are either notoriously difficult to dedicate accurately and fairly to a specific product or asset, or they occur broadly across all phases of the product lifecycle in a way that makes it really challenging to isolate their precise impact on one asset's LCC compared to another. The focus instead is squarely on the cost directly attributable to the asset itself, from cradle to grave, providing a clearer financial picture of that asset's individual economic journey. Other analyses might look at those broader costs, but standard LCC usually doesn't.
Got it. And maintenance, you keep rightly highlighting it, is clearly an enormous portion of LCC, especially given how long these railway assets operate. Can we break that down even further? What are the key drivers within that massive maintenance cost category?
Absolutely. And it's worth breaking down because it's often where the biggest savings can be found. For railway rolling stock, in particular, maintenance costs are profoundly influenced by the manufacturer's initial design decisions. Things like how easy the components are to access and replace, or how inherently robust and durable they are designed to be. But operators also have significant levers they can pull to influence these costs through their maintenance strategies and execution. We can effectively break these costs down into two main categories: preventive maintenance and corrective maintenance. So for preventive maintenance costs, which are the scheduled, proactive tasks designed to prevent failures, these are primarily driven by a few key factors. First, the interval of the maintenance task. This is huge. A longer interval between specific tasks means fewer times you perform that task over the asset's entire lifetime, which directly and significantly reduces the LCC. Operators, based on extensive experience, rigorous safety analyses, and technical feasibility studies, can sometimes strategically extend these intervals beyond the manufacturer's initial recommendation, if it's safe to do so. Even tasks with relatively short durations can have an enormous impact on LCC over a product's 50-year lifespan if they occur very frequently. Second, maintenance task duration and man-hours. This refers to how long it actually takes to perform a specific task and how much labor, in terms of skilled man-hours, is needed. The minimal duration is often fundamentally defined by the manufacturer's design. Some designs are simply much easier and quicker to maintain than others due to accessibility or component modularity. Third, material costs. These are influenced partly by the manufacturer's initial design choices, what specific components and materials they specified. However, operators can also influence these costs through smart negotiation with suppliers, maybe standardization efforts across their fleet to buy in bulk, and optimizing order sizes and inventory management. And fourth, the hourly rate for maintenance staff and machinery. This is defined by prevailing wage levels for skilled technicians in that region, and also includes the LCC analysis of the machinery and specialized equipment used within the maintenance workshops themselves. Those tools and facilities have their own costs. Then we have corrective maintenance costs. These are the costs incurred when something unexpectedly breaks or malfunctions. Reactive maintenance. These are primarily driven by, first and foremost, the failure rate of components. This is perhaps the single biggest driver of corrective costs. Higher reliability, meaning a significantly lower failure rate for components, translates directly to dramatically fewer corrective tasks needing to be performed, and thus dramatically reduces LCC. If something breaks less often, you simply spend far less time and money fixing it. It also reduces costly downtime. And second, similar factors as preventive: maintenance task duration, material costs, and hourly rates. These same factors apply when something breaks. When a component fails, you still need the labor, the replacement parts, and the time to diagnose and rectify the issue. These parameters, intervals, durations, rates, failure rates are meticulously defined, ideally, for every single critical component or subsystem. And then they're carefully aggregated, often using sophisticated models, to calculate the total maintenance costs over the life cycle. And just one final note here. It's important to remember that for a full life cycle LCC, looking cradle to grave, we generally don't consider any residual value for the asset, because the assumption is it's disposed of at the very end. However, If an operator makes a business decision to sell an asset mid-life, then its potential residual value is certainly a very important factor in their financial planning and decision-making for that observed span of the life cycle they manage.
Okay, this is where it gets really interesting for me. Where the rubber meets the road, so to speak, where theory truly comes to life. It's one thing to understand the framework and the cost elements, but how does this actually play out in real railway engineering decisions? Let's dig into some concrete examples. Can you share some?
Absolutely. Examples really bring it home. A fantastic case study involved a significant technology change for rolling stock, the introduction of the hydraulic axle guide bearing. Now, for anyone involved in railway operations, you know that wheel wear is a massive, massive driver of LCC for rolling stock. It dictates how often you need to reprofile or replace wheels, which is expensive. Conventional axle guide bearings, the older style, typically have just one stable stiffness setting, which isn't really ideal for optimal performance in both navigating tight curves smoothly and maintaining stability on long, straight tracks at high speed. It's a compromise. This new hydraulic bearing developed by Freudenberg Schwab is quite ingenious because it actually changes its stiffness based on the wheel set movement frequency. It becomes softer in sharp curves, which significantly reduces the forces on the wheels and the track, cutting down wear. But then it automatically stiffens up at higher speeds or on large radius curves to ensure good running stability. It adapts.
Okay, so improved performance, better dynamics. Sounds good technically, but what was the actual LCC impact? Did Swiss Federal Railways, who I believe evaluated this, see a real benefit?
They did. Yes, Swiss Federal Railways undertook a thorough LCC analysis specifically for using this on their passenger coaches. And the analysis for this technology change identified impacts across several key areas. Some adding costs, naturally, but others delivering significant savings. First, there were the upfront project management and homologation costs. You can't just bolt on new tech in railways. Introducing any novel technology requires managing the project carefully, undertaking extensive test runs, conducting rigorous safety assessments, preparing detailed documentation for regulatory approval, all of which, understandably, had costs initially. Then, the installation costs. The new hydraulic bearing itself is inherently more expensive than the simpler conventional one. That's a direct cost increase. However, critically, its interfaces were cleverly designed to match the old bearing's mounting points. This meant no major vehicle modifications were needed for installation if it was done strategically during a routine bogie overhaul, which is when the old bearing would typically be at the end of its service life anyway. So primarily, it was the higher product price of the new bearing that was the main LCC impact here, not significant extra installation labor. Similarly, for bearing maintenance costs, the required visual inspection interval and the duration of that inspection remained largely the same as the old bearing, and no higher failure rate was expected based on testing. So again, mainly the higher purchase price of the new hydraulic bearing impacted the maintenance LCC here, not increased ongoing maintenance efforts directly related to the bearing itself. It wasn't expected to need more attention. But here's where the significant game-changing savings truly came in. This is what made the LCC analysis look so positive, despite the higher upfront cost. A huge impact was seen on wheel maintenance. The reduced wheel rail forces resulting from the hydraulic bearing meant that the wheels experienced substantially less wear. This directly extended both the intervals for wheel turning, what we call reprofiling, reshaping the wheel profile, and also the intervals for full wheel exchanges. Fewer reprofilings and fewer full wheel exchanges over the train's entire lifetime led to very substantial cost reductions, both for the maintenance tasks themselves, labor, machine time, and for the logistics and downtime associated with conveying coaches to and from the workshops for these activities. Think of trains being available to earn revenue more often and needing less time stuck in the shop. That's a big win. There were also noticeable savings identified in energy consumption. Now, wheel wear fundamentally means energy is being consumed to remove material from the wheel surface through friction and plastic deformation at the contact patch. So logically, a reduction in wheel wear directly translates to reduced energy consumption during the train's operation. That's a continuous long-term saving that adds up significantly over decades of running. And interestingly, there were also tangible benefits calculated for the track maintenance costs. Less force being exerted between the wheel and the rail also means reduced wear and tear on the infrastructure itself, on the rails. This, in turn, was projected to lead to lower track maintenance costs for the infrastructure manager, such as less frequent rail grinding or potentially longer rail life before replacement.
Wow, that sounds like a clear win-win-win on so many fronts. Reduced wheel wear, lower energy use, less track damage. Seems like a no-brainer. But if it's such a no-brainer, and maybe I'm being naive, but why aren't all railway companies jumping on board immediately? What's the hidden friction here? Were there any complexities in making the decision that the LCC analysis might have revealed beyond just the numbers?
That's a fantastic, very insightful question. And it highlights one of the inherent systemic challenges in applying LCC analysis effectively within the modern, often fragmented railway sector. You see, not all LCC impacts, even powerfully positive ones like the track savings, were considered directly for the financial decision by the rolling stock operator in this specific case. Why? Because the reduction in track maintenance costs primarily benefits the infrastructure manager, who is often a completely separate legal and financial entity. It doesn't directly hit the operator's bottom line. So the rolling stock operator pays the higher upfront cost for the new bearing, but a significant chunk of the system-wide benefit, the holistic LCC reduction, accrues to a different organization's balance sheet. This is a classic example of those conflicting goals of legal entities that we discussed earlier as a major challenge for system-wide LCC optimization. The operator pays, someone else gets some of the savings. That can make the business case harder for the operator alone.
Ah, okay, that split incentive problem, I see.
Exactly. However, there is a very positive trend emerging in the industry to try and address this exact disconnect: the implementation of wear-dependent track access charges. In systems where these are in place, if an operator's trains demonstrably cause less wear and tear on the track, perhaps because they use technology like these hydraulic bearings, they actually pay less in track access charges to the infrastructure manager. This mechanism could allow operators to directly benefit financially from their investments in LCC improvements that also benefit the infrastructure. It effectively helps internalize those system-wide savings, aligning the incentives better. It's a really promising development. And it's also worth noting, just as an aside, that this new technology also happened to reduce noise emission from the wheel rail contact, which is a significant societal benefit for the communities living along the railway line. But this environmental benefit is typically not quantifiable as a direct cost reduction in a standard LCC analysis, even though it's a huge positive outcome from an engineering perspective. LCC focuses mainly on the direct economic costs.
That's a perfect segue, actually, into another massive driver of LCC wheel wear itself, but maybe looking at it from a different angle. What about changing the quality of the wheel material itself? This seems even more complex because it involves such a deep, fundamental interaction between the vehicle and the infrastructure.
It is indeed. And this is another excellent example where LCC analysis is absolutely critical, maybe even more so because of that deep interaction, the wheel-rail contact. It's one of the most highly interactive and dynamic systems in all of railway engineering. It's fascinating but complex. Its LCC is influenced by this incredibly complex interplay of factors: the specific material properties of both the wheel and the rail, their precise geometric shape, the vehicle dynamics, how the train moves and vibrates, the track geometry, curves, gradients, and of course the operational conditions like speed, axle load, traction, braking forces. Wear and degradation, the slow damage accumulation of both the wheel and rail materials, directly drives substantial and recurring maintenance costs. Things like reprofiling wheels, grinding rails to restore their shape, and eventually their outright replacement when they reach their wear limits. These are huge cost buckets. And you're absolutely right, this is precisely where that multi-entity challenge, the split between operator and infrastructure manager, really comes into sharp focus in a profound way. When railway companies are divided into independent undertakings, say, a train operator focused on running trains efficiently, and a track infrastructure manager focused on maintaining the track cost-effectively, decisions are often made based solely on the business case for one subsystem. For example, a new wheel material might be absolutely fantastic for extending wheel life, saving the operator money. But if that harder wheel material causes significantly more wear on the rails, increasing the infrastructure manager's costs, it could actually be a net negative for the overall railway system's financial health. This kind of fragmented approach, if it's not managed through a holistic LCC perspective, can unfortunately harm the overall financial viability of the entire railway system. So any LCC analysis for changing wheel material must proactively and comprehensively consider the effects on both the rolling stock, the vehicle side, and the track, the infrastructure side. You have to look at the total system cost. Okay, so to handle this complexity and try to ensure an optimal system-wide outcome, a structured LCC analysis for something like a wheel material change would typically involve several key steps. It needs a careful approach. First, you need the establishment of the organizational context. This means clearly recognizing that complex interplay of parameters influencing wheel-rail contact. And critically, acknowledging upfront the challenge of divided responsibilities between the operator and the infrastructure manager. The objective here has to be clear from the start. to rate the material change for a business decision based on its impact across the entire railway system, not just one part of it. Then you move to planning the analysis. Now, to perform this kind of integrated LCC analysis accurately, you need deep, specialized knowledge about the reactions, the likely effects on both affected railway subsystems, the rolling stock and the track. How will each respond to the new material? If existing data from previous tests or maybe operational use of the new material elsewhere is available, it must be rigorously checked for validity and relevance to your specific conditions. Can you trust that data? If no such robust database exists, then a pretest or a controlled trial might be required just to gather the necessary input data for the key parameters, wear rates, friction coefficients, etc. And that trial itself would need to be meticulously planned as a project. And since we're often rating a material change that happens during an ongoing life cycle, the analysis must consider the economic effects from the point of introducing that change right up to the very end of the planned life of the affected rolling stock and the track sections involved. Next, the definition of the analysis approach. As we've established, the wheel and rail interface is an interactive system, so the effects on both subsystems must be considered in a coordinated way. You can't look at them in isolation. A valuable first step here is often to use a model simplification process. This typically involves building up something like a two-dimensional decision matrix. This matrix essentially plots a proposed change, like our new wheel material, in terms of its likely negative, neutral, or positive effects on both the vehicle LCC and the infrastructure LCC. You assess the impact on both sides. For example, if a new wheel material shows a strong positive effect on vehicle LCC, longer wheel life, and a negligible or maybe even neutral effect on infrastructure LCC, doesn't wear the rails much more, then the matrix clearly signals that the change is strongly recommended from an overall economic standpoint. Go for it. Conversely, if one subsystem sees a significant negative effect, or if both are just neutral from an LCC perspective, then the modification should probably only be implemented if it's legally mandatory, or may be driven by overriding safety concerns, not purely for economic motivation based on LCC. This simplified matrix helps guide whether a much more detailed, resource-intensive LCC analysis is even worthwhile pursuing for certain scenarios. It's a quick check. If that simplified approach gives a green light, then you move to the application of an integrated LCC analysis. This means adopting that detailed cost breakdown structure we discussed earlier, but applying it meticulously for each influence subsystem, the vehicle A and D, the infrastructure, so you can transparently compare them side by side within the same model.
Now, every application of an LCC model depends heavily on its specific objectives and application area. In the wheel-rail interface, even subtle parameter variations in materials or geometry can lead to continuous physical effects, like wear. These should ideally translate to steady cost reactions that are captured accurately in your LCC model over time. However, it's also vital to account for discontinuities in maintenance planning. This is a subtle but important point. For example, extending wheel life only truly saves LCC if it allows you to actually skip planned maintenance activities like a full reprofiling visit to the workshop that involves taking the train out of service. It doesn't save as much if the wheel physically lasts longer but still needs to be dismantled at the same time for other unrelated bogey maintenance reasons. You have to consider the whole maintenance schedule. So for evaluating a new wheel material specification, it's typically recommended to run a detailed LCC analysis for the existing baseline material first, and then run parallel analyses for each specific new material option you're considering, comparing the total system LCC for each. Next, we move to the performance of the analysis. This is where each cost element, for both the vehicle and the infrastructure sides of the equation, is meticulously determined and inputted into the integrated LCC model. Because you're dealing with an integrated model involving potentially two separate subsystems and maybe two different organizations' data, you need to establish a consistent scaling unit right from the very beginning. This could be something like total annual cost, or maybe specific operational indicators like cost per gross ton kilometer and vehicle mileage for rolling stock, and cost per gross ton kilometer and track length for infrastructure. You need a common yardstick. It's also absolutely crucial to perform plausibility checks throughout the process. Are these numbers realistic? Compare your results with historical data or established industry benchmarks if they exist. And a comprehensive sensitivity analysis is vital here, especially to clearly show the importance of the impact on infrastructure costs, which might otherwise be downplayed or overlooked by a rolling stock operator focused only on their immediate vehicle budget. This sensitivity analysis helps reveal where the biggest levers for system-wide savings truly lie. Then comes the finalization of the analysis. At this stage, the focus is squarely on clearly estimating and presenting the differences in cost elements between the various alternatives being compared. For example, new material versus baseline. What's the delta?
Remember, as we discussed, the LCC analysis itself typically doesn't directly include capital costs or financing aspects. Its focus is on operational expenditure and through-life costs. Therefore, to get a truly complete financial picture for making a major investment decision, like switching materials across a whole fleet, it's often necessary to consider annual interest rates and discount factors to evaluate the net present value, or NPV, of the different options. NPV helps us factor in the time value of money, seeing what future costs and savings are truly worth in today's terms. This is absolutely critical for comparing long-term investments fairly. And finally, just like any good LCC process, the update of the analysis. An update of this kind of integrated wheel rail analysis might be triggered when several situations occur. Maybe a completely new technology emerges in either the wheel or rail subsystem. Maybe key input values significantly change, like a drastic sustained shift in steel prices or energy costs. Or perhaps new environmental regulations introduce new cost flows or incentives related to wear or noise. For frequent business planning processes, regular updates might be essential to keep the LCC information current and relevant for ongoing decisions. However, if an analysis was performed solely to make a specific one-time decision about, say, adopting a particular new wheel material, it might not need frequent updates unless one of those significant triggering factors arises later on.
Okay, so this all sounds incredibly powerful, truly a comprehensive tool for making smart long-term decisions in a very complex environment. But I have to say, it also sounds like a truly massive undertaking, potentially fraught with challenges and maybe even some pitfalls. What are the practical limitations or the real hurdles when trying to implement these complex LCC analyses in real-world railways? It can't be easy.
No, it's definitely not always easy. You hit on a critical point. While LCC theoretically aims for the absolute minimal total cost over an asset's life, achieving that perfect optimum in practice is incredibly complex, and it faces several inherent challenges. First, there's the sheer complexity of the breakdown structure itself. A truly exhaustive cost breakdown structure covering all potential costs for a railway asset that lasts 50 years is incredibly intricate. Just mapping it all out is hard. This complexity can inadvertently lead to problems like double counting costs, where a cost element might mistakenly be allocated to multiple categories, inflating the total. Equally problematic, and often more insidious, is the risk of missing important cost elements entirely. Things like the indirect costs associated with non-availability of an asset during an unexpected breakdown, lost revenue replacement services, or the extensive time and resources spent on root cause analysis for recurring failures. These often aren't planned costs in a direct sense, but can be substantial. Capturing everything is tough. Second, there are often significant information gaps and estimation needs. Let's be realistic. Not all necessary information is always readily available or perfectly quantifiable, especially when you're trying to project future costs decades into the future. What will energy cost in 2050? What will labor rates be? This means some parameters must be estimated based on the best available data and expert judgment. But this inherently introduces uncertainties into the analysis. You're trying to predict the future, and that's never perfectly clear. So the LCC result is always an estimate, not a certainty. It requires expertise and careful judgment in making those assumptions. Third, the long lifetimes and market changes for railway assets present a truly monumental challenge. We're talking about assets, trains, track, bridges, signals that can last 50 years or even more. Predicting input values like material prices, energy costs, labor rates, technology evolution, or even the overall economic and market situation over such incredibly extended periods is extraordinarily difficult. Forecasting becomes less reliable the further out you go. This leads to inherent uncertainties in long-term LCC forecasts, making them more of a robust estimation within a likely range rather than a precise point prediction. It's like trying to forecast the weather 50 years out. You can see trends but not specifics. And fourth, as we've touched on several times, a very significant and persistent challenge is the conflicting goals of legal entities. As we discussed with the wheel and axle examples, different legal entities, rolling stock operators, infrastructure managers, manufacturers, maintenance providers, all influence LCC at different life cycle phases. Each entity naturally tries to maximize its own benefits or minimize its own costs, which is rational from their perspective. But this can sometimes be in direct contradiction to optimizing the LCC of the entire product or the entire railway system over its lifespan. This fragmentation can unfortunately lead to suboptimal outcomes for the railway system as a whole if it's not managed strategically through contracts and incentives.
Right, so it's clearly not just a technical calculation problem, it's a systemic and even an organizational one, too. Given all these profound challenges, the complexity, the uncertainty, the conflicting goals, How do companies navigate this? How do they still ensure that LCC analysis delivers genuine significant value despite the imperfections?
That's the key question, isn't it? It means recognizing that LCC analyses and their results are an incredibly powerful input for financial planning and decision-making. But they're almost never the only input. You can't make decisions based solely on the LCC number in isolation. You also need to consider other crucial financial factors like the potential revenues generated by the asset, its possible residual value at the time of disposal or maybe a midlife sale, and importantly, the initial capital expenditures required and whether the organization actually has that capital available. For decision-making between alternatives, focusing only on the differences in cost between those alternatives, as we discussed, significantly reduces complexity. It makes the analysis far more manageable and actionable because you don't get bogged down trying to quantify every single tiny cost element that's the same for all options. And even if available funds, say, limit you from choosing the alternative with the absolute lowest theoretical LCC, perhaps because it has a prohibitively high acquisition cost that you just can't afford, right now performing the LCC analysis still enables a truly balanced decision.
You go into that decision with open eyes, fully understanding the trade-offs you're making between a lower upfront investment and potentially higher long-term costs down the line. A structured LCC breakdown, even if it's not perfectly exhaustive, is absolutely key to a systematic analysis. It helps reduce those inherent uncertainties by providing a clear, logical framework for your financial thinking and exposing the long-term implications of short-term choices.
That makes perfect sense. It's a tool for informed trade-offs, not just finding the single right number. But that last point you made about conflicting goals between different entities, the operator versus the infrastructure manager, for instance, that still seems like a really deep-seated challenge for the industry. Is there a way forward? Is there a way for the industry to better align these goals to truly benefit from LCC on a systemic level?
This is perhaps one of the most important strategic questions for the future of the railway industry as a whole, especially in liberalized markets. To truly improve LCC across the entire system, methods are absolutely needed to better incentivize all the different entities that define or impact costs throughout the asset's lifecycle. This means actively finding ways to reward them for achieving lower total LCC, not just focusing narrowly on, say, lower acquisition costs for the manufacturer or lower operating costs for the operator without considering infrastructure impact. Examples we've touched on include operators explicitly choosing products with demonstrably low LCC in their tenders, even if the initial acquisition cost is somewhat higher because they recognize the long-term system benefit and value. That sends a strong market signal. Another key area is the continued implementation and refinement of mechanisms like those wear-dependent track access charges we talked about, where operators whose trains cause less wear and tear on the infrastructure are financially rewarded for that positive externality. These kinds of approaches help foster the development and adoption of innovative products and operational strategies that might indeed be more expensive initially, but deliver significant system-wide savings and benefits over the asset's entire life. It's really about creating an economic ecosystem where long-term value, efficiency, and sustainability are collectively prioritized and rewarded across all stakeholders, breaking down those silos. It's a journey, but a necessary one.
So, wrapping this all up, what does this really mean for us? We've seen today that railway lifecycle costing is so much more than just looking at the initial price of a new train or a signaling system or a section of track. It's far deeper than that. It's a comprehensive, systematic approach to understanding every single cost from the moment an idea is conceived right up until that asset is disposed of, potentially decades later. It's fundamentally about making smarter, more holistic decisions, decisions that lead to profound long-term efficiency and sustainability for the whole railway system, even when dealing with the inherent complexities of different legal entities, incredibly long asset lifetimes, and the undeniable challenges of predicting the future. It's about truly understanding the total cost of ownership, isn't it?
Exactly. And if we connect this to the bigger picture, particularly for those of you studying or starting careers in this field, LCC analysis ultimately challenges us, as engineering students and professionals, to think beyond the immediate transaction, beyond just the technical specifications or the elegance of a design on paper. It pushes you to consider not just the technical brilliance of a new design, but its long-term economic footprint on the entire railway system. How will it perform financially over 30, 40, 50 years? It truly underscores that in railway engineering, every single design choice you make, every material specification you select, every maintenance strategy you help implement today has a significant ripple effect on the decades of costs to come. The crucial question for you as you step into or advance your career in this vital industry is this: How will you leverage the power of LCC thinking to shape the future of railway systems for optimal long-term value, efficiency, and sustainability, not just for short-term gains or the lowest upfront price? That's the challenge and the opportunity.
That's a powerful thought to leave everyone with, and a fantastic challenge for anyone involved in railways. This has been a really insightful deep dive into railway lifecycle cost. We truly hope you've gained some valuable insights and practical understanding that you can carry into your work and studies. Until next time, keep digging deeper.